Good afternoon. And well, this is to the NPTEL team. Are we online?
Yes, sir, we are on live.
Okay. Okay. So good afternoon, everyone, and welcome to the second session of live session of Gasdynamics fundamentals and applications. We have a question on chat. It is regarding the kind of problems for that are given during assignments and what is given during exams, and the use of gas tables. Well, in almost all the calculations of gas dynamics, we use gas tables extensively. Uh, we rather use gas tables than use uh, trying to solve equations using the calculator. So it is better to use gas tables, and in the test, gas tables which are relevant to the problems will be given. And we have actually cross-checked to see that uh, the questions can be handled during the exam. So I don't think there is going to be an issue in that sense. We have one participant. Good afternoon, Deepti Moon. It has to end, right?
Yeah. The assignment solutions will be uploaded after the submission date.
So now in the course, we are at fan of flow.
We are currently dealing with fan flows. So we have covered all range of oblique shocks, expansion fans, moving normal shocks, shock tube, variable area ducts, and currently we are doing fan of.
Fan of flow and rally flow.
Yeah.
After that, we are almost towards the end of the course.
Yeah.
So we have covered almost all that is important for the fundamentals of gas dynamics. I think we have a little bit more on MOC and some special lectures on
linear perturbation.
But, yeah. Those are some special lectures.
People were a bit having a misconception of, or you can say that they were unable to understand the concept of contact discontinuity in the shock tube.
Okay. So the contact discontinuity. Yes. So first thing is the shock tube analysis is done in an inviscid manner. Okay. So the initial condition of a shock tube is that we have two sections. One is the driver section, the other is driven section. Usually the driver section is at higher pressure and driven section at lower pressure. Besides that, there can be differences. The driver section can also have a different gas in practical shock tubes. It can also have different temperature. So the driven section essentially holds the test gas, and the shock is sent through the test gas, and we compress the test gas using the shock. So the contact discontinuity in some sense separates these two regions and continues to separate it during the dynamics of the shock tube, because it is an inviscid flow situation, idle flow situation. So since we can have different temperatures and different gases, the driver and driven, the contact discontinuity separates them. It's a fluid interface, it's not a solid interface. So in that sense, at the fluid interface, always the pressures and velocities are equal. And but you could have different, for example, temperatures or different densities. So that's fine. So that is the
board ball is that at the contact discontinuity, we see that the pressures are same across it and velocities are same.
Yeah.
So if we draw a control volume there, why are the mass flow rates different?
Yeah, mass flow rate, it need not be the same. It is an unsteady flow. It can be different. It's an unsteady flow. So if you draw you should actually analyze the whole control volume and look at how it varies in time. So you can also see that the slug of gas that is between the contact discontinuity and the shock, that is not a constant. It keeps changing. So in fact, the way you define the control volume also will vary. If you are considering, say, the compressed gas, the one, say, the gas which has a constant velocity U2 behind the shock, if you draw a control volume around that, you will see that keeps on extending larger and same way.
Say that from the end of driver section to contact surface, the gas which we have, that will remain, that mass will remain constant. And from contact surface to other end, that mass will remain.
Yeah, the integral. The
integral
mass. Integral mass can remain constant, but your mass flow rates and those can be changed. Integral will remain.
One of the question was regarding the mechanism. How does the shock reflect in a shock tube from the end?
Yeah, so the end wall reflection, like we discussed for oblique shocks also, the shock reflection is a nonlinear phenomenon where it has to, the gas dynamic equations of continuity, mass, and momentum, they are actually conserved, the all three of them, and the reflection happens in such a way that it satisfies the boundary condition at the wall. The wall boundary condition is that the flow cannot penetrate into the wall. So the moment the shock arrives at the wall, behind the shock, there is a mass motion of the gas. The shock will reflect at that particular point immediately. What should happen is the mass of gas that was moving with the shock behind it has to immediately stopped and made to go to zero. And this is all in laboratory frame, not in the frame of the shock. So in the laboratory frame, it has to it has to go to zero. So the reflected shock strength is in such a manner that it is moving into a gas which is already moving towards itself. And once the gas passes through the shock, it will achieve velocity zero in the laboratory. So that's the way the shock reflects from the end wall. The same principle that we use for oblique shock reflection also, that at the wall, the boundary condition is that there is no penetration into the wall.
गोल्डन स्टेट डेटाबेस का उसको पता रहेगा गोल्डन स्टेट डेटाबेस
So there was one more question that when are we normally considering the strong shock solutions for oblique shocks and conical shocks?
Usually, you observe strong shock solutions during shock interactions or shock reflection phenomena. During a normal, say, for example, you are designing, say, a diffuser using a series of shocks, or say you have an external shape, for example, the wedge-shaped airfoils, which is usually flying in ambient, that is in free stream. There we normally do not encounter strong shocks, because you also have to have the pressure ratio that a strong shock uh, gives at the downstream condition. The way we look at these problems is not just the um, changes in Mach number, but also whether downstream pressure conditions also have they are also met, especially when the shock goes strong, then the flow becomes subsonic after the shock, and then there is all the chance that the downstream pressure and the upstream can communicate with each other. So that means that when that happens, then there must be something happening in the downstream section. That usually happens either during the cases of, say, shock interactions, or also in the case of certain cases of strong shock boundary layer interactions. Then around the flow over them, you can find some separation shock and the impinging shock. They can interact with each other and produce max stem and such kind of situations. Or during irregular reflections, you can get max stem. The solution behind the max stem is in the strong shock. So that's where usually we find the strong shock solution, but not generally not over, say, the flow over a wedge or something.
According to every flow, which is basically a non-adiabatic flow. Please guide.
Yes, there is a question by Sunil Godbole on the sonic speed. The sonic speed is always a local property, and there is a standard definition to it, which is that it is the speed calculated using an isentropic process, right? Having dou P by dou rho, change of pressure to change of density. That is standard. In whatever flow you take, it is the standard definition of sonic speed. Even if there is, a flow in a duct is having a heat transfer. Okay. The heat transfer is going to affect the temperature of the flow. But the speed of sound at any local point is a well-defined property, which is dou P by dou rho at constant entropy. Okay, so what actually can be sort of understood in not only in Rayleigh flow, you can also see this in Fano flow and also in isentropic flow. We define a quantity called the M star, or rather we call it as the star property. Or what we say is that it is the property where at which the flow achieves sonic speed. Okay, so the flow is following a certain process and it achieves Mach number equal to 1. Okay, it does not mean that the definition of sonic speed has changed. All that it means is the route to reach Mach number 1 is different. It may seem trivial in isentropic flows because the definition of speed of sound is itself isentropic. But in both Fano flow and Rayleigh flow, we reach Mach number 1 through a certain process. In Fano flow, it is by friction of a duct. So as you increase length of duct, the flow accelerates and reaches 1. So what we refer to as the star quantity or the star pressure or star temperature is that point. That point will not be located on an isentropic line. And same way in Rayleigh flow, you will achieve Mach number equal to 1 by following a Rayleigh curve. At any point on that Rayleigh curve, you can define speed of sound, which is going to be, the definition does not change. Okay, so that is the understanding. So what we call as the star point, or where you achieve Mach number equal to 1, is different in Fano flow, it is different in Rayleigh flow, but not the definition of speed of sound.
I think the major doubt everyone has is when we define star properties earlier, we say that isentropically we have to get our gas to a Mach number of 1. But when it comes to these scenarios, we neglect that. We majorly focus on that Mach number equal to 1 condition.
Yes.
So,
See, in an isentropic flow, you can define a star value. In that flow, that star value is achieved by an isentropic process. So in the same way, during a Fano flow, you can define a star value. But now how do you achieve that star value? It is through a Fano curve. So when we deal with isentropic flow, we say it is isentropic. When we deal with Fano flow, we say it is going along a Fano curve. And when we deal with Rayleigh flow, we say it is going along the Rayleigh line. So the definition of stagnation properties and the definition of speed of sound, they are all based on hypothetical processes and they do not change in any of this flow. In any of this flow, if you want to find the stagnation property, or you want to find speed of sound at a certain point, this is always a standard definition. Okay. But
so if we reach Mach number equal to 1 in a process, might be anything. So then we can say that is
a star condition. That's a star condition. And what we see is that star condition is unique to that particular process.
We have another question. What are difference between pressure vacuum type tunnel and in-draft type wind tunnel? One is it's open and closed. Any other differences?
Yeah, pressure vacuum tunnels and in-draft wind tunnels. It's not just that. Okay, what you mean by open is the in-draft is drawing the air directly from the ambient. So in an in-draft tunnel, you will have high vacuum in the vacuum tanks. And to start the tunnel, you would open a valve which separates the test section from the nozzle and the test section from the vacuum tank. And once you open that valve, the atmospheric air is sucked in. While in a pressure vacuum type tunnel, you will also have high pressure that is attached to the nozzle and the test section upstream of the nozzle, and vacuum will be on the downstream. Why we have these different kinds of facilities has to do with the need to simulate different flight conditions or different flow conditions that one encounters during an actual flight or in a certain operation. So for certain kinds of what you should understand is that what we call as simulating is to look at getting certain Reynolds numbers and certain Mach numbers right. So if it is based on dynamic similarity, and we would like to get on a wind tunnel test model the same kind of Reynolds numbers and Mach numbers as is encountered in flight. If we do that, then we can say that the coefficients of, say, forces like normal or axial forces, or it can be lift and drag, they can be transferred on to the actual larger system also. So since we have a wide range of operational Reynolds numbers and Mach numbers, we have to simulate that range. Then the requirement is different in different sections. So that's why people use different kinds of facilities. So you can actually put all of them, all different kinds of facilities on a Reynolds number, Mach number graph and look at what they can simulate. So it is in that context that we have different facilities. And it is also a difficult choice because you will find that in trying to get, say, one parameter correct, say, trying to get simulate Mach number right, it becomes very difficult to simulate Reynolds number. Or if you try to simulate Reynolds number, then it becomes very difficult to simulate Mach number. So there is no one particular facility where all of them can be simulated together. And in an actual flight, it's just not only Reynolds number, Mach number. You may need stagnation enthalpy. You may need so many other simulations or non-dimensional numbers to be simulated. So that is the whole. That's why it's called ground test facilities. Rather, you can put them. That's why we have pressure vacuum wind tunnels, in draft wind tunnels, Ludwig tunnels, then shock tunnels. We have a variety of them because no one facility can simulate all possible conditions.
One question was in convergent divergent nozzles. We see that there are cases of overexpansion and underexpansion, where you have all the structure shocks and expansion constraints. But in some cases, we say that there will be a shock sitting inside the divergent portion.
Yes.
So, how do we come across such kind of scenarios in actuality where a shock sits in the divergent? Or
Yeah,
is it just
you
a
get
model?
no, you get shocks in the divergent portion. You get it in what are called as severely overexpanded nozzles. You could, yes, you could get them. We also observe them in our experimental facilities, especially when you have the starting process of a nozzle. During that time, you observe that if no special care is taken uh, to quickly drive away the starting shock. So in some of the facilities, what they do is create a good amount of vacuum so that the starting shock is immediately swallowed. Okay, that in that sense, we may see those states. It will still be present, but it may go away as a transient. But in some other points, you can actually see that the shock takes a while to travel from the divergent portion out and then generate a complete flow. You also observe this, say, for example, these kind of shocks. These are what we can call as internal shocks. The internal flow shocks can also be observed as a response to the back pressure in the ducts. Suppose the device, say whether it's a nozzle and a duct, or some of them are connected to some other downstream device, and that downstream device is imposing a back pressure onto the duct. Then also, if the conditions do not match properly, especially pressure conditions, then that can generate a shock. That
Considering only a converted divergent nozzle,
Mm.
if we ensure a back pressure, normally when we model the shock standing inside the divergent portion, we find some back pressure. We
Yes,
find some
yes,
pressure
yes.
after the shock. So if the back pressure is maintained to same level,
Mm.
will we have a shock standing inside the divergent portion, or will we have a case where the flow exits but exhibits all the shock? Or
So yeah, so in a real flow, there is the boundary layer which is always present in any device. For example, even in nozzles also. So in that sense, what happens is once the pressure increases beyond a certain value, then what we start getting is actually flow separation due to shocks within the nozzle. And that can proceed to go upstream as the pressure keeps increasing. So the state of the flow is changed in some way. So what you could also have is a large separation. So the core flow is now no longer expanding all the way to the area of the duct. So the Mach numbers might be different. Within the core flow, you could have some strong oblique shocks, and sometimes they can also be a Mach stem kind of shocks. So those are called as shock trains, and that is a complex behavior. But if you take a shock train in its entirety and apply the conservation of mass, momentum, and energy equations around the shock train, then you will find that they satisfy the normal shock condition. In fact, if you allow the shock train to fully form and you find the pressure ratio across it, you will almost reach something like 85 to 90% of a normal shock's pressure value. So because of that, as a simplified model, we can actually look at having a model as a normal shock inside the bath. So it is a good model to understand what is happening in a in a classroom sense, or in a sense of understanding. But when one is going to real flows, then there are complexities which are modeled in a different. Anything on the YouTube?
For UAVs are different from those for aeroplane models.
What are you making a statement that they are?
A question that whether they are different or the same.
Mm, yeah, so it is. So now UAVs have different scales. Some of the UAVs are actually as big as a small aeroplane itself. So what you have to look at is actually scaling. But what we could, an interesting question is whether test facilities for MAVs are different from that of larger models, larger scaled models. So that has to do with Reynolds number scaling. So MAVs have very small scales. So it is a completely different scale from, say, larger aircrafts, even a generic aeroplane. Okay. So then you shift Reynolds number range. Reynolds number range for commercial airliners and all is greater than 10 millions. Okay, and for a smaller aircraft, it would be in the range of millions. Okay, so but for MAVs, you may suddenly find it is about 100 times lower than 100 or even 1,000 times lower than those numbers. Then we may encounter some different or interesting flow phenomena. So yeah, so for different Reynolds number regimes, we need different facilities. Okay. So if you are looking, so there are fundamental sort of wind tunnels. One is, of course, looking at having something to test an object. Like there are wind tunnels which are large enough to test small aeroplane models directly, scale direct, or even 1:1 scales. There are such large wind tunnels do exist. While many research wind tunnels ask more questions like what happens when the Reynolds number is in a certain regime. Okay, so then people look at even changing the fluid. It need not be air itself because you are simulating Reynolds number. So if you're simulating Reynolds number, then you could actually change the fluid, get a Reynolds number of what is required, and then ask a question. Say if I take a standard airfoil, NACA 0012, and then what happens to the flow around this airfoil when the Reynolds number is not in the range of, say, 1 million. then you have to build a different facility for doing that.
Choice of wind tunnel or any tunnel that you are choosing to test your model depends upon the flow features that you are trying to
Yeah, yes, flow features, because as the Reynolds, even when you take, for example, a cylinder and you change its Reynolds number range, even from very small ranges to, yeah, so from creeping flow and you go all the way, you observe different phenomena.
Yeah.
So if you want to test them out, your wind tunnel should have the capability to produce that Reynolds. So you have to do that.
And that facility with leading setup, it differs from wind tunnel. For designing open net facility to achieve Mach 1.5, what are parameters should we consider? That we should consider.
Open jet facilities. Oh, I just from what I understand from your question is just an atmospheric. We call it as atmospheric blowdown facility. Yeah, right. So for cold flow, so it is just you have high pressure on one side and it is opening out into the atmosphere. Such a facility is called a blowdown facility or atmospheric blowdown facility. So the pressure that to which it is exhausting is the ambient pressure. So there you can your control or you have a control only on the stagnation pressure which is built up on using your compressors. So uh, that depends on what Mach number that you want to consider. You can look at the pressure that you have to have in the reservoirs. Usually, what we do is reservoirs will have somewhat higher pressure, and then we use a flow regulating valve to reduce the pressure to what is required so that you have because if you want just the pressure for a certain Mach number, then you will be able to operate only that Mach number. So usually these facilities are designed to have a range of Mach numbers. So the pressure vessel you cannot keep changing to for different Mach numbers. So what we do instead is have a common pressure vessel and then have a flow regulating valve to change the pressure. So that's all that we do in a blowdown kind of facility.
Small question in the discussion group, where a person was asking if we have a supersonic flow in a duct with friction. So basically fan of flow. So when do we see that there is a shock formation in the duct, and which is the case where it changes its curve?
Okay, so yeah, so the shock formation in a long duct, what we see is um, we could look at it like in uh, maybe this question we'll answer first. Uh, I think we already discussed this in the initial part of the live session that for the exam, whatever data is required will be given in the question paper itself, and the gas tables can be utilized extensively for solving the problems, and you don't need to carry a gas table with you. And the question of you see that we are always analyzing a flow after it has been established. In all these processes, the flow establishment also plays a strong role in where the shock is situated. So often they do not have unique solutions. So when we analyze these kind of solutions, what can be done is that we can consider a range of locations in which shock is present. And then we can always the goal is that if the flow is subsonic downstream, then the downstream back pressure should match the exit pressure. So to locate the shock in that sense is like you consider a range of possible locations of shock, or then continue to apply the condition that at the downstream the pressure is matching the back pressure. Then we will get a location of the shock. So what we should understand is that we need a boundary condition, even though the incoming flow is supersonic. Okay, but if you are not given the boundary condition downstream, then you have not been given enough data to look at the problem, to analyze a problem. Then it becomes like you can give a best possible solution to the problem. So if you are not given what is downstream, so once the flow becomes subsonic, you need an information on the downstream if there is a shock. So if that is also not given, if you're just given that, okay, the duct is there and a flow is entering, say at Mach 1.5, length of duct is so and so, and there is a shock somewhere in them, only so much. Then you cannot give a unique solution to this problem. The shock can exist anywhere in the duct, and as it changes its location, you can have different pressures that develops on downstream. So that is the way. So
There was one more question that in fan of flows, we normally neglect the effects of temperature. There is no heat addition or heat removal from the system.
yes.
And in relay flow, we do not consider the friction factor.
Yes.
So what happens if both the factors are present? How do we analyze the system? Because the major analysis that we do in these systems
Yes.
are if we have friction in our momentum equation, then the curve which we form are by the means of momentum, continuity and energy equation. And in the other case also.
Yeah. So Fanner flow and Rayleigh flows, as well as say varying area duct flows. All these are separated in order for us to understand a general flow by understanding the. So you can look at them as a forcing given to the flow, and by different means, different kinds of forcing. Like you can vary the area of the duct, or you can have a long duct, means that there is friction. It does not mean that there is no friction in the nozzle or a varying area duct, but the dominant effect there is due to a varying area of the duct. Same way, when there is lot of heat addition, one of the ways of this happening is like if something is burning inside a duct and you consider that that is releasing heat, or it need not be burning. Suppose there is a phase change occurring, like you, that also is releasing heat, and the flow is happening within the duct. Then there, a lot of heat can get released quickly. Then the dominant effect becomes the addition of heat or the removal of heat. Um, so then if you consider all of them are not there, but you have a long duct, any long duct will have effect of friction. So to understand, um, we are grappling with, even if I just consider a compressible flow with none of these, but includes a shock, it is already a complex flow. So, if you have to understand the flow, to get an understanding of the flow, we actually classify the flow into these template or standard flows, so that you understand, okay, what is the effect of friction, what is the effect of varying area flows, and you in some sense get an understanding of what happens. So the overall understanding will not change. When there is a supersonic flow and you add heat to it, pressure will increase and Mach number will decrease. But now if you also have friction and also include a area change, okay, you will have the sort of addition of multiple effects. They are not going to, you cannot simply say, okay, it is 1 plus 1 equal to 2. They are not going to behave in that manner. So you have to solve the equations. We do consider them in a generalized manner. So there are, you can set up the whole equations using control volume analysis, just like we did for, varying area ducts. So you consider a completely general case. You include all forcing, and they lead to an equation called the generalized quasi-1D, where you can include all these effects. Okay. So some things which we can, some of the interesting results that we see in them is, suppose we consider area change and friction together. Then what we see is that in an area change, um, the convergence of the area actually drives it towards Mach 1, right? From a subsonic flow. It drives it towards Mach 1. Similarly, friction also drives it towards the Mach 1. And we know how we argue these out using the influence of dA by A. Then we also have the influence of f dx by d. Okay, so these influences, if we add them together, then you will see that there are competing influences of dA by A and friction. So because of this, if you look at how Mach number changes, if you include both of them, you'll find that the location of Mach number equal to 1 point will be slightly different in a convergent divergent duct when we consider both area change and friction, it is located slightly in the diverging portion, slightly downstream of the minimum area. But that is only very slightly downstream. So, how much different or how big a difference does it make in estimating? So, the why we do all this is these are very good estimates to start, say, designing a nozzle. If I have to get, say, a Mach 2 flow, there is a certain area ratio that I have to get. There might be a slight increase in the area ratio if you account for boundary layer and things like that. So these effects, I would say, is second order. So first order dominant effect is due to the area change. So then after that, we can add on the effect of friction. So like that, you can iteratively solve for an actual problem which has multiple effects. It is done in generalized quasi 1D analysis. But that is, I would say, advanced gas dynamics problem.
Are there any commercial packages in CFD domain for working out the combined effects of Rayleigh-Fano area reduction as you explained?
So see, when you go to a full CFD, you are actually including all of them. You don't need to separate them. You can include all of them and you solve the equations. But I don't know about commercial packages, how it is actually implemented. But whatever implementations that we have seen, you can have a wall boundary condition which includes a heat transfer. You can include viscous effects through RANS or laminar flow models. Yeah. You can use a RANS model or a laminar flow model, depending on the Reynolds number. You can use it. So automatically you have combined everything. You don't have to separately do it. I think it is 50 minutes into the. You can look for another 5 more minutes and.
One more doubt was, sir, we discussed that in oblique shocks. To cancel the oblique shock, we turn the wall away from the flow direction such that it matches its deflection angle.
Yes.
Are there any other methods also which can cancel our oblique shock?
See, oblique shocks are formed. Why do they form? One is you have some flow deflection condition, a flow turn. There is a need for a flow turn. Then you get oblique shocks in that situation. Or the other one is a response to a pressure condition that is needed. Sometimes both are together. Often it is together. So if we nullify the need for a flow turn, then automatically there is no need for an oblique shock. But the strength of the oblique shock can be changed or can undergo a change when there are interactions with, say, other waves like expansion. So when expansion waves come and impinge onto the so for example, if you take the wedge in a free stream flow, or say a wedge shaped airfoil, which has, say, it's an isosceles triangle, then the forebody will produce a shock, but at the tip of the isosceles triangle, it produces an expansion. We normally look only at what happens to the body, but now if we look at what happens to the flow in the free stream, then you will find that the oblique shock, it's a discontinuity, it can continue for a long distance. But then the expansion fans also, they continue into the flow. It's a supersonic flow. They can continue. But then these two can actually come and meet. When they do meet, then it can change the strength of the shock because the expansion waves are turning the flow away from the direction of. So that way you can modify, or if you want to aerodynamically alter the flow in a certain way, then you can shape the passages in order to produce or nullify some of these shocks or expansion. So that is how you would do it as an aerodynamic design. Yeah, thanks. I think we have had a couple of good discussions from the members. Well, and so it is towards the end of the course. Now, more or less, the topics are all special topics. It's for additional knowledge and to increase awareness on the different applications of this interesting area, and also towards directions where current research is going on and what is interesting in these domains. So people can continue looking at looking at the course ahead and derive some benefits out of it. But I think we have covered more or less all the core gas dynamics course is almost all complete. Thanks, one and all. I think